Hey guys, and welcome back to another video. In this video, we will be talking about geometric sequences and series. So recall how in the last video we discussed arithmetic sequences and series. And remember that an arithmetic sequence is defined if there's a common difference. Okay, so a geometric sequence then is one that has a common ratio. And we usually denote common ratio as R. And we denote common difference as D. Okay. So a common ratio is essentially now you're multiplying every previous term to get the next term. So for example, if we had 1, 4, 16, 64, and so on, this would be a geometric sequence because each time you're multiplying the previous term by 4 in order to get the next term, right? Whereas in the arithmetic sequences, you were adding, but now you're multiplying. So that's like the main difference between geometric and arithmetic sequences. All right. So now let's get right into it and let's derive the general term of a geometric sequence. So same thing as last time, right? The first term, and since we're dealing with geometric sequences, I'll call it G instead of A. So the first term will be G1, and that is equal to G1 times nothing, right? So we'll say like R to the power of 0, so that's just times 1. And then G2 is just the previous term, which is G2 is just the previous term, which is G1 times R, right? G3 is the previous term, which is G2 times R. But we know what G2 is in terms of G1, so we can just write this as G1, and then R times R is R squared. And then G4 is just G3 times R, but we know what G3 is, it's just G1 times R squared. So this just becomes G1 R cubed. And this process just continues. But I think we can see a pattern just from these four terms. It's a pretty similar pattern to the arithmetic sequences. So if we take Gn to be our general term, then notice that the all of these have the form G1 times R to some power. Now what power is it? Well, notice if it's G sub 4, it's the fourth term, then the power of R is 3, which is exactly 1 less than 4. Similarly, here is G3, the power on R is 2, which is 1 less than 3. 2, the power on R is 1, which is 1 less than 2. And then here is G1, so the power is 0, which is 1 less than 1. So it seems that if we have the nth term, then the power on n is just, or power of R is just n minus 1. Okay? And then, of course, we can generalize this even further. So we get Gn is equal to G sub k times R to the n minus k. And this is the general term of a geometric sequence. Okay? All right, good. Now let's do some practice problems. So let's say we're given a sequence 2, 10, 50, 250, and so on, right? So, and we want to find the seventh term. So we want to find G sub 7. So first we have to see if this is a geometric sequence or not. So from 2 to 10, this time instead of seeing what we add, we have to see what we multiply by. So 2 times 5 is equal to 10. 10 times 5 is equal to 50. And then 50 times 5 is equal to 250. Okay, so each time we're multiplying with the same number, so it's geometric. And our common ratio is 5, since that's what we're multiplying by. And our first term is 2. So then if we use the formula, Gn is equal to Gk times R to the n minus k. Gn, we want G7, so n will be 7. Gk, k will be 1 since you know what the first term is, times R, which I'll not substitute anything in yet, and then n minus k, 7 minus 1. Okay, so G7 is what we're trying to find. G1 we said was 2, and then R is 5, and 7 minus 1 is 6. So if we evaluate this, we should get 31250. So this is the 7th term of this geometric sequence. All right, good. Okay, let's do another example. So example 2. So let's say same thing for arithmetic sequences. Let's say now we're given like a couple of terms and we want to find the common ratio and the first term. So let's say we're given that the 5th term is 0.01 and we're given the common ratio is 0.1, and we want to construct the sequence using this information, right? So first I'll just write down the formula again. Gn is equal to jk times r to the n minus k. We know what r is, it's 0.1, and we know the 5th term. So in order to construct a sequence, what do you need? Well, you always need the first term, g1, and you need the common ratio. Well, we know what the common ratio is 0.1, so now we just need to find the first term. So if we set n equal to 5, since we already know what the 5th term is as well, and then we set k equal to 1, since we're trying to find the first term, and then we can solve for the first term from there. So I'll say n is equal to 5 and k is equal to 1. So this becomes 5 minus 1. And now g5 is 0.01, g1 is what we're trying to find, and 0.1 to the 4th power. So in solving for g1, you get 100. So we know that g1 is equal to 100. So now that we have the first term and the common ratio, we can construct this sequence, right? Because we start at 100, and then each time we're multiplying by 0.1. Or this is essentially the same thing as dividing by 10, right? So this is equal to dividing by 10. So if we divide this by 10, this is equal to 10, then 1, then 0.1, and then so on. Okay, good. All right, so now let's move on to geometric series. So unlike arithmetic series, where arithmetic series, remember how we discussed that those are always finite, right? Because if you have an arithmetic series, let's say 1, 3, 5, 7, and so on, the only way for this to converge is if it's finite. Because if this is an infinite sequence, then this is going to, or this should be series. So 1 plus 3 plus 5 plus 7 plus da da da. So the only way for this to converge is if it's finite, because if this was infinite series, then it would just diverge. However, for geometric series, even if it's an infinite series, it can converge under special circumstances. But first, we'll talk about finite geometric series. So a finite geometric series has this general form. Right? So these are just like the terms of a geometric series, and we're just adding them all up. But we can rewrite this as g1 plus g1 times r plus g1 times r squared plus da 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 plus g1 times r to the n minus 1, right? And then what I'm going to do is I'm going to multiply this whole equation by r on both sides. So we get r times s of n is equal to g1r plus g1r squared plus g1r cubed plus da 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 plus g1r to the n. And then let's subtract these equations. Okay. So on the left-hand side, you get s sub n minus r times s sub n. And then on the right-hand side, notice something really cool happens, right? Because this g1r minus this g1r, that cancels. g1r squared minus this g1r squared, that cancels. And then over here, there'd also be a g1r cubed, so that would cancel with this. And then right before this term, there would be a g1r to the n minus 1, so that would cancel. So all these terms in between just cancel. And so then the only thing you're left with is g1 and then minus g1 r to the n, right? So now we can do a couple of factoring. So on the left-hand side, we can factor out a sn, and you get 1 minus r. And then on the right-hand side, we can factor out a g1, and we get 1 minus r to the n. And then solving for Sn, we get g1 times 1 minus r to the n all over 1 minus r. And this is the formula for a finite geometric sequence or series. There is one restriction though, is that r cannot equal 1, because notice that if r did equal 1, the denominator equals 0, and dividing by 0 is undefined. But yeah, all right, let's do some practice. All right, so let's say we had the sum as k goes from 1 to 13 of 3 times 0.4 to k minus 1, right? So if you know the general term of a geometric sequence, it's that, right? And this matches this perfectly, right? Because gk is 3, r is that, and then you have n minus 1, k minus 1. So just from that, you can be sure that this is a geometric series. And it's finite because it's only going from 1 to 13. So if we apply our formula, we have Sn is equal to g1 times 1 minus r to the n all over 1 minus r. And n is 13 because we have 13 terms. The first term, just plug in k equals 1 into this. You should get just 3, because this 1 minus 1 is 0, and then 0.4 to the 0 is just 1. So just 3 times 1, which is 3, times 1 minus r, the common ratio is 0.4 to 13, all over 1 minus 0.4. So evaluating this, you get approximately 4.999. Alright? Alright. Let's do another one. So let's say we want to find the first 9 terms of 1 plus 2 plus 4 plus 8 and so on, right? So this one is a geometric, because each time to get the next term you multiply by 2. So right off the bat, we can see that our common ratio is 2, and we know that our first term is 1, and we want the sum of the first 9 terms. So S sub 9, and that's equal to the first term, g1, which is 1, times 1 minus the common ratio 2 to the power of n, which is 9, all over 1 minus r. Okay, and again, just evaluating this, put into your calculator, and you should get 511. Okay? Alright, nice. Alright, so now let's move on to infinite geometric series. So, infinite geometric series. So let's take the formula for a finite geometric series, right? So it was like S sub n is equal to g1 times 1 minus r to the n all over 1 minus r, right? So now, infinite geometric series, that just basically means that n is like infinity, right? So we'll take the limit of this as n approaches infinity of this thing, and let's see, what do we get? So if we were just like to informally like kind of plug in infinity, you would get S sub infinity is equal to, so r to the infinity, right? That's just like so there's two cases, right? So one is like if absolute value r is less than 1, and then one is absolute value r is greater than or equal to 1. So notice that if r is greater than or equal to 1, we have r to the infinity. That's just going to go to infinity. and then 1 minus that, that's going to get negative infinity. So basically, if r is greater than or equal to 1, infinite geometric series will never converge. On the other hand, if r is between 0 and 1, so essentially it's a fraction, then we have a fraction to the power of infinity. That's going to get smaller and smaller, so that will just approach 0. So for this case, r to the n, that's just basically saying 0, because r to the infinity is 0. So here we just get g1 on top, 1 minus 0 is just 1. And on the bottom, we have 1 minus r, because that doesn't change. So that's the special condition that I was talking about earlier. So this is the formula for an infinite geometric series, but infinite geometric series only converge when absolute value of r is between 0 and 1. And that should make sense too, right? Because let's say we had this following series, 1/2 plus a fourth plus an eighth, and so on. Clearly, like every single time you're adding on a smaller fraction, so it seems like it should approach some value, right? Because it's not like, at least not clearly blowing up to infinity. And it doesn't, right? It will approach some value. All right, good. So now let's do some practice. All right, so let's say we're given a series 1 plus 1/3 plus 1/9 plus 1 over 27, and so on. So first of all, is this a geometric series? Yes, it is, because each time, notice that we're multiplying by 1/3, right? So it's a geometric series, and it's infinite, right? Because this continues on forever and ever. So now we have to check if it converges or diverges. Well, it will converge if the common ratio is between 0 and 1. So the common ratio in this case is 1/3. So if the absolute value of the common ratio, so the absolute value of 1/3, is less than 1, it is, right? And so that means that this will converge. So then we could just apply the formula that we have, right? So S of n is equal to the first term over 1 minus r. So the infinite series is equal to the first term, which is 1, over 1 minus the common ratio, which is 1/3. So you get it's equal to 3/2. So I think that's pretty cool how like an infinite series can just converge to some value. All right, let's do another one. All right, let's say we're given a series that's equal to the sum as n goes from 0 to infinity of 2 times negative 1/4 to the n. So first of all, is this a geometric series? It is, right? Because we have a each time we're multiplying by the common ratio, which is negative 1/4. And if like the index is in the exponent, that's a very strong indicator that it is a geometric series. So we can, and then it's an infinite series as well, right? Because we're going from 0 to infinity. So we have to determine if it converges or diverges. Well, r is equal to negative 1/4. And so absolute value of r, that's just 1/4, which is less than 1. Check, right? So meaning this does converge, so we can just apply the formula. So it's equal to S sub infinity is equal to the first term over 1 minus the common ratio. And here we have the first term. If you put 0 into here, we just get 2. And then 1 minus the common ratio is negative 1/4. So 1 minus negative 1/4. And if you were to evaluate this, you would get 8/5. Right. All right, cool. And then just like an example of a geometric series that doesn't or that diverges would be like if you had let's see, 3 plus 15 plus 75 plus 375, right? Indeed, this is a geometric sequence, right? Because notice how each time we're multiplying by 5. So it's a geometric series for sure. But the problem is r is equal to 5. So absolute value of r is less than 1. No, it's not, right? So that means that this diverges. Okay? All right, good. So yeah, that's pretty much everything about geometric sequences in a series. If this video was helpful to you, please make sure to subscribe so you don't miss any future videos. And other than that, I'll see you guys in the next video.